In the last video, we have seen that projective varieties are naturally pre-varieties in the sense that we had before with a sheaf of regular functions. And as I said, we now start very slowly to approach the proof that these are actually varieties. But it turns out for this proof, it's actually really useful to first consider what are the morphisms of these projective varieties. Because once we have a pre-variety structure, we know what it means to be a morphism. And here we're going to see the advantages of the approach that we have taken to projective varieties, defining them from scratch as sets and topological spaces and so on, because we could have gone this route of gluing. We could have gone this route of first constructing Pn by gluing together the affine spaces An, and then saying a projective variety is a closed sub-pre-variety of Pn. But the advantage that we have now is that we will not have to do compatibility checks on overlaps, as you have to do for gluing. And also, it turns out many morphisms have a global description. You don't need to specify them on each open patch and then check that they agree on overlaps. But in fact, you can give one global recipe. And this is the next lemma, so morphisms of projective varieties. So if you have X inside Pn, a projective variety, and then you have m+1 elements of the homogeneous coordinates ring, which are homogeneous of the same degree. Then, I mean, in principle, you would like to write down a map from some open subset of X to Pm, whose coordinates are just given by this F0 up to Fm. And this works. Turns out this gives a morphism. And exactly the locus where it gives a morphism is the complement of the common vanishing locus of these, of F0 up to Fn. So somehow once these are not all zero, then you get a well-defined element like this. So this gives you a big class of morphisms to some projective space. And then of course, if they factor through some closed subset here, then you also get the morphism to this closed projective variety in Pm. And so first of all, let's check that this is a well-defined map of sets. So exactly because we restrict X to lie in U, so not all of these functions vanish at the same time. And so this vector here is not the zero vector. And so this gives some element of projective space Pm. And then the independence of scaling X just follows since all the Fi are homogeneous of the same degree. So if you take a different representative, there's X by lambda X, and you get out a global factor lambda to the degree of these functions. And this is killed by the scaling on Pm. So we do get a well-defined map of sets. And to show that it's a morphism, we now don't go this route of like showing it's continuous and so on, and then checking regular functions, because we can actually just check this on an open cover. So somehow we have seen some gluing property of morphisms. So if we find an open cover of U, such that the restriction of F gives you morphisms to the target there, then you also get a proof that F is a morphism. And we obtain this open cover by starting with an open cover of Pm, and then taking the pre-image, and then checking that these restrictions are all morphisms. And for the cover of Pm, we just take the standard open cover, and we call it now Vi to distinguish it from the pre-images. So somehow let's say Vi is the set of points in Pm such that the ith coordinate is non-zero. This gives you an open cover of Pm. And then the pre-image under this map, well, this is just saying the ith component of the map gives something non-zero. So this just says that Fi of X is non-zero. And we see, first of all, as a good sign, that this is just U minus the projective vanishing locus of Fi. This is indeed an open subset of U. Okay, so we have reduced the thing that we want to check to checking that the restriction of F going from Ui to Vi is a morphism. But then in the last video, we showed that these Vi are actually isomorphic to Am, and we wrote down a particular morphism F, which we call F inverse, in this direction from here to there. And this F inverse just took this vector y0 up to ym, and then just replaced the coordinates here by y0 divided by yi up to ym divided by yi. Okay? But this means if we now take this composition, this f upper I, then what it just does is composes these two things, and so it sends x to this vector here. And you note somehow there's one coordinate in the middle, which would be fi divided by fi. This is omitted. So this gives you really m different functions here. And then this was an isomorphism. So checking that this is a morphism is equivalent to checking that this here is a morphism. But now we have a map to am. And we see that the coordinates of this map, they're quotients of polynomials of the same degrees, homogeneous. And so these are regular functions on this UI by the definition of the sheaf of regular functions that we had last time. And the claim is then a map to am whose components are given by regular functions is a morphism. Now, to be fully honest here, we proved this statement in this proposition here in Gutmann's notes. We proved this when the domain was an affine variety. But in fact, the same statement on the nose is just true when the domain is a pre-variety. And either, I mean, maybe you have checked this as part of some exercise, or, well, I mean, the check is not super difficult because the pre-variety is covered by affine varieties. You can check if something is a morphism on a cover, and then once you restrict to that cover, it's just the proposition that we had here. So in any case, we have reduced from general case to the case of morphism to am, and this we understood very well, and so we could check that this is indeed a morphism. So somehow we have already a big class of morphisms to projective space just given by m+1 homogeneous functions of the same degree. And we'll start now looking at some examples of these things, particular classes that we can always write down and which are very useful to have. The first talks about maps from Pn to Pn itself. So, and the claim is we can write down such things very nicely if we are given the data of a matrix, an n+1 cross n+1 matrix, which is invertible over K. This means A is in this GL n+1 K, the general linear group. And then once you have this, the claim is you can write down f from Pn to Pn, sending x to A times x. And just you basically interpret this as a vector with n+1 entries, and then you just take the matrix multiplication here. So the first observation here is that this fits the criterion for the proposition that we had above. Because, well, the entries of this vector by the formula for the matrix multiplication are just this kind of sum of aij times xj. The aij are constants given before, and the xj now are just linear polynomials. So you see all the components here are homogeneous of degree 1. So by the proposition, you get a morphism like this on the complement of the vanishing locus of all of these things. And here our claim is that this complement of the vanishing locus is actually all of Pn. To see this, well, assume you had this matrix A such that A times x is 0, which is the same thing as just requiring all its components to be 0. Then, since A is homogeneous, it would force x to be 0, but x is never allowed to be 0 inside Pn. So this shows that this is a well-defined map on all of Pn. And we claim even more, it's not just a morphism here, but in fact we claim it's an isomorphism. And the inverse is now easy to write down. The inverse is just given by the inverse matrix. Clearly, if you compose these two maps, you get the identity in both ways. And so this shows that this is indeed an isomorphism with this given inverse. And we call these maps the projective automorphisms of Pn. If you recall, an automorphism is an isomorphism from a space to itself. And so this name fits. And there's a cool fact, namely that every automorphism of Pn is of this form. So it's a complete classification. We should note one thing. There's some slight ambiguity which we want to get rid of. So we had A is inside this GL n+1k. But we noticed something with this recipe. Let's say A was, for example, just a matrix which is a multiple of the identity matrix, just lambda, 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 and so on. Then you see A times X is just lambda times X, which is just the same thing as X itself. And so somehow for this scalar matrix, we would get the map X maps to X inside Pn. And so this would be the identity matrix. So even though the matrix is not the identity matrix, it would be sent to the projective automorphism, which is the identity. So somehow scaling this matrix in general doesn't really change this map, right? If you replace A by lambda times A, you in general get the same map like here, because the lambda in the scaling of Pn can just be removed. And so what you can do is you can define PGL n+1k, the projective general linear group, to be just a quotient of this here by an equivalence relation, where you say any matrix is equivalent to the scaled matrix lambda times A, where lambda is a non-zero constant. This is the projective general linear group, and it's indeed a group. The multiplication law is just you take the equivalence classes and multiply them together, like this. And then by the argument, which we have seen before, in fact, if you are just given the equivalence class of A inside PGL2, in fact, this projective automorphism F given here is independent of the choice of representative. So this means there's a map from PGL into the automorphism group, sending A to this automorphism F above. And the big claim here and the fact, which we're not going to prove here, is that this is an isomorphism of groups. So somehow the automorphism group of Pn is exactly this PGL n+1k. And that's a really cool statement. These projective automorphisms are really useful because they really allow you to move points around inside Pn very concretely. And also maybe as a remark, we had discussed before the automorphism group of A1. This was pretty simple. And then I told you that the automorphism groups of A2, A3, and so on, they're extremely complicated groups. They're not very well understood. So these are very, very difficult to understand. On the other hand, the automorphism group of this projective space is very simple. We can just write it down. It's just some matrices. So that's another kind of general theme, that once you have projective things, then things like automorphisms groups are much better behaved than in the affine case. So this was a first example of some projective morphisms. And next video, we are going to continue with another important construction in this area.